This is Gemini 7 as seen from Gemini 6 during man's first rendezvous in space. Later, Gemini spacecraft performed rendezvous with other vehicles, including inert objects previously placed into Earth orbit, and the primary target, the restartable Agena rocket. The experience gained in Gemini can be applied to the Apollo program. The ability of one spacecraft to rendezvous with another already in orbit is vital to the success of the lunar mission. To understand the part that Lunar Orbit Rendezvous plays in a manned lunar mission, we must first review the overall mission plan. The lunar spacecraft will lift off from the Earth and go into orbit about it. At the proper time, the spacecraft will inject onto its lunar transfer trajectory. As the spacecraft approaches the Moon, it slows down and goes into lunar orbit. The spacecraft actually consists of two separate vehicles: the command module, which remains in orbit around the Moon during the period of lunar exploration, and the lunar module, in which two of the three Apollo crewmen will descend to the lunar surface. After a period of lunar exploration, the astronauts will lift off in the ascent stage of the lunar module. Rendezvous and dock with the command module, retransfer to the command module, and return to Earth, leaving the ascent stage in orbit around the Moon. Lunar Orbit Rendezvous, then, is a key part of a manned lunar mission. Some practical limitations on its accomplishment include the accuracy of the guidance and navigation system, the amount of propellant that can be carried by the lunar module ascent stage, and the ability of the flight crew to perform the numerous and complex tasks involved. Another factor is the tracking ability of the ground support system. Ground-based computers transmitting through the ground support system supply fresh information to the computers carried on board the lunar and command modules. The only time contact with either module will be interrupted is when that module is behind the Moon. In order to understand the nature of this rendezvous, it is necessary to understand basic concepts and terminology involved. For instance, the command module is in orbit about the Moon. The lunar module is in a lower orbit. If we draw a line from the lunar module to the center of the Moon, and another line from the command module to the center of the Moon, the resultant angle is called the phase angle. The altitude difference between the orbits is called the height differential. The height differential and the phase angle are descriptive of the relative positions of the command and lunar modules during the rendezvous. Together, they are termed the phase-height relationship. Now, the lunar module in the lower orbit will circle the Moon more rapidly than the command module in the higher orbit, since the lower orbit is a shorter path around the Moon, and the spacecraft in the lower orbit moves with greater angular velocity. It can therefore be seen that the lunar module will catch up with and would eventually pass the command module. As the lunar module catches up with the command module, the phase angle naturally gets smaller. But the lunar module is actually in an elliptical orbit. Therefore, as it catches up with the command module, it is also climbing toward it. thus decreasing the height differential. When the phase and height differentials become zero, rendezvous is accomplished. The rendezvous plan selected has evolved from previous flight experience. It is called the concentric rendezvous plan and works like this. The command module is always in a known location in orbit relative to the lunar module on the Moon. When the phase angle is optimum, the ascent engine is ignited and the ascent stage, using the descent stage as a launch pad, lifts off. The ascent engine is cut off once the lunar module has achieved a safe coasting orbit. At a given interval after the launch cutoff, the first planned maneuver called concentric sequence initiation is made. The engine is fired so that the lunar module is placed into a new elliptical orbit. At the highest point, or apolloon, of this new orbit, the lunar module will be at a desired phase-height relationship below the command module. At the predicted time of apolloon, the engine is once more fired and the orbit adjusted so that the height differential between the two orbits remains constant during the coast. This is called the constant delta height maneuver, delta in this case standing for differential. When the lunar module and the command module are in the proper relationship, the third planned maneuver called terminal phase initiation takes place. This will lead to the intercept of the two spacecraft. We are now ready to take a detailed look at the concentric rendezvous flight plan. The first thing we want to know is what time to lift off. Lift-off time is dependent upon where you want to rendezvous with the command module and the time it will take to fly the rendezvous. The orbital position at which you want to meet the command module is dependent primarily on the desired lighting conditions for each phase of the rendezvous. Therefore, a number of important factors come into play. For instance, there are three basic areas of illumination of the lunar surface. There is the area lit by direct sunlight, the area lit by sunlight reflected from the Earth or earthshine, and the area on which neither sunlight nor earthshine fall, the dark area. The command module must be able to track the lunar module with optical instruments, so that in case of emergency, the command module pilot could fly to the lunar module to perform a rescue. If you were in the command module looking for the lunar module, a flashing beacon on the lunar module could be seen from about 500 miles away against the dark side. Against the Earth-lit surface with less contrast, the beacon would be visible up to about 250 miles. And with the low contrast against the sunlit surface of the Moon, the lunar module could be spotted by its reflected sunlight at a distance less than 50 miles. And there are other lighting constraints. The command module, in sighting the lunar module through its optical sextant, must never have to look for it at an angle of 10 degrees or less to the sun. An accidental look at the sun through the high-powered sextant could blind the astronaut. During the final braking maneuvers prior to docking, neither module must have a line of sight from the other that will cause the crews to look out their windows within 30 degrees of the sun. From these and other lighting conditions, it has been determined that the point of terminal phase initiation should come within a fixed region prior to entering darkness. With a nominal position fixed, and given a fixed time span from terminal phase initiation to rendezvous, we can then determine the optimum point of rendezvous. Now, knowing the liftoff point on the Moon, the position at which we want rendezvous to occur, and being able to calculate the time it will take the lunar module to fly the rendezvous, we can determine the liftoff time. When the correct phase angle is reached by the command module, the ascent engine of the lunar module is ignited, and the ascent stage lifts off the surface of the Moon. There are two objectives which determine the nominal liftoff time. First, the desired constant height differential, which is to be achieved between the lunar module orbit and the command module orbit. Second, the lunar module must arrive at terminal phase initiation at the nominal time, this time being dependent on the lighting requirement. The liftoff time and subsequent burn are designed to accomplish these two goals. The burn into orbit will last approximately 7 minutes. The lunar module now enters its first coast period. During this coast, the crew will make appropriate navigational calculations and systems checks. The next maneuver to be performed is concentric sequence initiation. This burn will have only one objective: to adjust the catch-up rate of the lunar module to bring it to the point of terminal phase initiation on time. The concentric sequence initiation burn places the lunar module in an elliptical orbit around the Moon. Regardless of normal accumulated errors, the computed time of arrival at the high point of this ellipse, calculated prior to concentric sequence initiation, is the time the constant delta height burn will be initiated. This burn will give the two orbits a constant height differential. It is probable that this will not be at the exact apollune, again due to normal errors. This is to keep the crew's time schedule predictable and uncrowded. The objective of this constant delta height burn is to achieve a constant height differential between the orbit of the lunar module and the command module. Now let's look at the phase height relationship to see the result of the constant delta height maneuver. Once this has been achieved, that is, when the lunar module orbit remains at a constant altitude below the command module, the phase angle becomes smaller, but the height differential remains the same. If we draw a tangent to the lunar module orbit at the position of the lunar module, this is called its local horizontal. The elevation of the line of sight between the lunar module and command module is referred to this local horizontal and is called the elevation angle. Since the height differential after the constant delta height maneuver remains constant, the proper phase height relationship for the subsequent transfer can be detected by one correlating factor: the elevation angle. This can easily be recognized by the crew. The elevation angle used as a trigger for terminal phase initiation is 26½ degrees, which gives nearly optimum use of propellant when coupled with a standard intercept transfer orbit of 130 degrees, corresponding to a standard intercept time of approximately 42 minutes. When the elevation angle is 26½ degrees, the flight crew fires the lunar module engines for terminal phase initiation. The length of this burn is directly proportional to the height differential of the two orbits. Also, the transfer arc, coupled with the elevation angle, provides a direction of thrust along the line of sight from the lunar module to the command module. These factors make it easier for the crew to monitor the burn and facilitate backup procedures. This path of 130 degrees means, too, that the lunar module will always approach the command module from below. This is extremely helpful from the point of view of the final braking maneuvers. For a fuller understanding of terminal phase initiation and the subsequent approach, we imagine that the lunar module is at the center of a coordinate system. The location of the lunar module represents the point of terminal phase initiation. This axis represents the height differential between the lunar module and the command module. Since the command module is above the lunar module, it will be in the upper half of the system. This axis represents the distance ahead or behind the lunar module of the command module. Since the command module is ahead of the lunar module, it will be located in this quadrant. Since terminal phase initiation occurs when the elevation angle is 26½ degrees, the command module must be located on this line, the line of sight. If we did achieve our nominal height differential of, say, 15 miles, then the command module will be located here. Now, what if the constant height difference between the two orbits was not nominal? Let's say that the actual constant delta height achieved was 17 miles. The command module must still appear along the 26½ degree line of sight. The same thing holds true if the height differential is less than the nominal 15 miles, say 13 miles. The terminal phase initiation burn will be programmed so that the time of theoretical intercept will always be at the same time after terminal phase initiation. This is theoretical intercept since it does not take into account terminal braking maneuvers for docking. The standard time to intercept will be about 42 minutes. Using the lunar module as a point of reference, the point from which the astronauts will see the rendezvous, the command module will appear to follow a course like this. It will appear to the lunar module crew to approach them, pass overhead, then come back along this path for the final docking maneuvers. 10 minutes after terminal phase initiation, the command module will appear along this line of sight. 20 minutes after terminal phase initiation, the command module will be seen along this line of sight. Again, the time of travel from terminal phase initiation to theoretical intercept will always be the same. Now let's say we did not achieve the nominal height differential. If we were higher, the command module would appear to follow this course. Lower, this course. Since the time to fly this course will always be the same, regardless of differences in height differential, at any given time, the command module will appear along a given elevation angle or line of sight. This can be seen directly by the flight crew and is used to monitor the guidance and navigation system. Reviewing then, to determine the liftoff time, we need to know where we want the lunar module and command module to rendezvous. This will be determined by lighting conditions. Computing the total time of the rendezvous sequence will give us the liftoff time. At liftoff, the lunar module is trying for a nominal constant delta height and a nominal time for terminal phase initiation. The lunar module will be inserted into a safe orbit around the moon. After a specific time interval comes the concentric sequence initiation. This maneuver will adjust the catch-up rate to arrive at terminal phase initiation at the nominal time. The constant delta height maneuver will occur at a time predicted as a part of the determination of concentric sequence initiation. The constant delta height maneuver is designed to achieve a constant height differential between the orbit of the lunar module and the command module. Following this, the computer can predict the time of arrival at the next maneuver point, terminal phase initiation. When the elevation angle between the lunar module and the command module of 26½ degrees is achieved, the crew fires the lunar module engines to achieve a standard intercept time. The concentric rendezvous plan is also applicable for contingency situations. For instance, if the lunar module is at the beginning of hover for the landing sequence and an abort becomes necessary, the ascent stage separates from the descent stage and goes into a safe orbit. Concentric sequence initiation will occur at the normal time. The constant delta height maneuver will also occur at the nominal time. However, an option in the computer program allows terminal phase initiation to occur one orbit later. Since the lunar module will remain in a lower orbit for a longer time, it will catch up with the command module and be at the correct phase-height relationship with the desired lighting conditions for terminal phase initiation. Among the advantages of the concentric rendezvous plan are efficient use of the propellant that can be carried, simplification and standardization of crew tasks and sufficient time for accomplishment of these tasks, optimum use of onboard equipment, and maximum integration of the data and communications facilities of the ground support system. It also allows for absorption of normal errors and facilitates backup rendezvous procedures. The accomplishment of Lunar Orbit Rendezvous is a vital portion of the Apollo lunar landing missions. The concentric flight plan provides a flexible, unhurried, and simple method for its accomplishment and can be easily adapted to contingency situations, thus helping to ensure the success of this major step in man's exploration of space.